We will now discuss this idea. Yeah. Resource partition. So see, in FPGA we have programmable logic, right? So we will use some part of those logic for designing one convolution layer engine, CLE. Now one CLE will process one convolution layer at one time, and now the same hardware, same piece of logic will be used for processing next layer. Okay, but different layers have different dimensions. So using a fixed CLE dimension for all the layers will lead to poor efficiency. For example, if your CLE is such that it can multiply 3x3 matrices, but if next layer requires 5x5 multiplication, then this 3x3 multiplication layer will not be very useful. Here is an example. So VG16 is very nice CNN because it has uniform kernel size in all the layers. Also, it has power of 2 number of input and output feature maps, except for the first convolution layer. Whereas LXNet, it has variable kernel sizes. Okay, in some layers it has 11x11, some layers it has 5x5, some layers it has 3x3. So that means for VG16 we don't need to do this optimization, but for LXNet, using a fixed CLE for all the layers will lead to poor efficiency. So here is an example. If accelerator has only single CLE, then throughput on mapping VGG16 will be higher than that with LXNet. Okay, so here is an example. So first of all, left side is results on LXNet. Right side is results on VGG16. Okay, and here area 10 is the name of the FPGA model. Okay, area 10 is the name of the FPGA model, just like we have Xeon version 3 for the CPU and so on. So area 10 is the name of the hardware. Now there are these are different research techniques: DNN Weaver, LMO, Sys Array XL, Intel DLA, this FPGA 2017, and so on. So these are the research techniques. Okay, so if we use these research techniques, which all use single CLE, and implement on the same FPGA, first you implement LXNet and then you implement VG16. So usually you will see that VG16, by using VG16, you get more operations per second. Even though FPGA is same, right? FPGA is same, but if we implement VG16, we can do more operations per second. That should not happen, right? Ideally, I mean, the operations per second we can do on a single FPGA should be same, or at least quite similar. But here, this is much larger. So here, the paper we are reviewing, their idea is to use a multi CLE design. Okay, so how to do that I will show very soon. So here we partition the resources across multiple smaller CLEs that closely match the layer dimension. That means even if our total resources used are same for single CLE design and multi CLE design, but in multi CLE we are using those resources to make multiple smaller CLEs. So let us see an example. So for example, this is a simple illustration. Here, this is the dimension of layer L1. This is the layer L2. These are not the caches. Okay, L1, L2, L3. These are also used for caches, but here they're not caches. This L1 is the dimension of the first convolution layer, and so on. So this is the single CLE approach where even if we have a larger CLE, so all the hardware we have used in just one CLE, all the resources we had, for example, all the LUTs or DSPs we have used in a single CLE. Okay, so first we use it to process or compute the layer L1. Some hardware is unused, then it very well matches the layer 2 dimension, so fine, no problem. For L3 is quite big, so L3 cannot be processed in a single in one go. So you have to do that processing in 2 goes. That means 2 steps. In the second, our total number of compute resources are still same, but we have partitioned it into 2 CLEs, which can operate in parallel. So first we use the first CLE to process L1. Now the wastage is less. Okay, because CLE1 is smaller than this CLE, so the wastage is less. Here, this is CLE2. which is used for layer 2. Then the first seal is now used for L3, then again layer 3, and meanwhile, in 3 steps, layer 2 processing can be completed. Okay, so here you can see that instead of 4 steps, we have completed everything in 3 steps. So our time is saved. So performance is improved. So now, as you can see, for VGG16, we don't need this approach because VGG16 has regular kernels. The kernel dimensions are same in all the layers. But in LXNet or those CNS where the layer dimensions are quite different. Okay, filter dimensions are quite different. There, this technique is quite good. Okay, any questions? Here is use of multiple FPGAs. So the point is, because each FPGA has very limited resources, single FPGA cannot efficiently map large CNNs. Okay, so that's why they propose using deeply pipelined multi-FPGA design. That means use multiple FPGAs and connect the output of one FPGA with another FPGA. That means you can execute one layer on one FPGA, another layer on another FPGA, another layer on another FPGA, or multiple layers on FPGA if your network is very, very deep. For example, there are some CNNs which have 90 convolution layers. So you can have, for example, if you have 5 FPGAs on each, you can have something around 20 or 18 layers. And we have to find, then the goal is to find best mapping of every CNN layer to an FPGA so that overall throughput is maximized. Because there is some transfer overhead. When you transfer the data from one to another, these links are much smaller. I mean, they have much lower bandwidth. So, so you don't want to unnecessarily split or unnecessarily use more FPGAs. As little as possible number of FPGAs, that's what you want to use. Okay, so here is an example design. So here we have 6 FPGA boards which are used for CNN computation. And here these are the 6 FPGA boards, and this is one Xilinx board which serves as a controller. So actually, when we come to brainwave design, so there also they will show how multiple FPGAs are used. But there we are not going to talk so much about hardware. Here we are showing the hardware feature. There actually Microsoft is mostly a software company. So there we are talking more about the software interface. Here this figure shows you the hardware design also. I mean, it's not like a very close to the hardware design, but somewhat at least some hardware you can see. Now, finally, we can use heterogeneous computing. So if you remember, GPU was working as a device and CPU was the host. So you could offload some of the computations on GPU, and GPU does your costly computation. Similarly, we can have FPGA is also an accelerator. So it sits as a device. CPU always acts as a host. Now here is another level where, see, Intel has purchased Altera. So now Intel is designing both CPU and FPGA. And similarly, AMD has purchased Xilinx, if you know. So AMD is now designing CPU and FPGA. So now you can see all the CPU companies have captured the FPGA companies also acquired. So now the whole purpose is, instead of having, see, conventionally we connect CPU with FPGA over the PCI Express slot, and that is very slow. So here the idea is, let us design, because both of these are same companies, so they can themselves design a system where FPGA can access Xeon's cache also. Okay, so they can access Xeon's cache also. That means it's a tighter integration. And the system memory can be addressed over a fast high bandwidth link. So now the point is, because the transfer, the communication latency is greatly reduced, because this link is high bandwidth, right? Because PCI Express is quite slow. This is one thing you will see whenever you use PCI Express. Every time you will hear this from me, that PCI Express is quite slow. It becomes a bottleneck. That's why here, because it is now such a high bandwidth. So now this is much more efficient. So for example, we can run only selected portions of algorithm on FPGA where FPGA is efficient. When it is not efficient, we can use CPU. Okay, and because the link is very fast, so doing some of the things on CPU, some of the things on FPGA is not very costly. You can easily do that. right? So run remaining portions on CPU. For example, backpropagation algorithm may not be easily feasible on FPGA. So run it on CPU. So here is an example result from researchers from Intel themselves. They have published that Xeon plus FPGA design provides comparable throughput as a GPU design while providing better throughput per watt. Okay, so here actually in deep learning, your baseline has to be always GPU because CPU is anyway not so efficient. So they have shown that if you use Xeon plus FPGA, so that means why? Because FPGA is used only where it is very efficient. Otherwise, FPGA is not used. Otherwise, you use the CPU. CPU is quite good for certain operations, so use it. So that's why if you use the best of CPU and FPGA, it can match the throughput of GPU while providing better throughput per watt. Okay, so here are the tool flows. So most of them are actually research. These are not companies. Many of them are actually research papers. Okay, so here the point is previously actually CAF was quite popular. Now in recent years, TensorFlow and PyTorch, they are more popular. So for example, here the idea is you write your code in Torch or TensorFlow, and these tool flows will map it to the FPGA. Okay, these are the high level tools. Fine. You write your code in CAF or you write your code in Theano, it will map it to the FPGA. Now, here again, you don't have to remember this. So here we are trying to summarize what are the challenges in each of the CNNs. For example, LXNet, here the filter sizes are not uniform and it uses group convolution. ZFnet is has high computation requirement. Its memory footprint is quite high. DenseNet, it has irregular computations and it has irregular layer connectivity. So the whole point is, especially when you are designing an FPGA, you have to think a lot about hardware obstacles. So these design features can lead to hardware, challenges in the design of hardware. Okay, so we are not going too much deep into it because this course is not so much about the CNN design. This course is more about the hardware design. So how it causes irregular computations and irregular layer connectivity, that we are not going to deep on that. So now what are the future challenges for FPGA? So there are actually complex blocks. They break uniform connectivity. So for example, if you've heard about ResNet, so in ResNet there are residual connections. There are some linear networks where just one layer connects with the next layer, but there are some other CNNs like ResNet where layer 1 may also connect to layer 3. Layer 1 may connect to layer 4. So now the connectivities are no longer simple and uniform. Okay, so there are these lead to irregular layer connections. So this becomes little difficult on FPGA. Because on FPGA you have to think always about the hardware connections. Now next is how do we map sparse CNNs to hardware. So I will discuss sparse CNN next week. Okay, one of the presentation is left, but I want to discuss it after the after the exam, after the MT, whenever we come next. Okay, so because I want to keep this week little simple. Okay, so existing works support CAF and TensorFlow only, but there are newer frameworks. So the whole point, as I said before, in software level, you can very quickly advance, but to map those designs to hardware takes a lot of time, maybe 2 months, 3 months, 5 months, even for big companies. So that's why this FPGA mapping remains always lagging behind the software progress. And next is how to use FPGA for training. Right now, FPGAs are used only for inference. But nowadays there are actually very big FPGAs which have billions of transistors. So probably they can be used for training, but still it's a challenge because the bandwidth is less. And how do you especially use it for low precision training? So these are some of the challenges for FPGA. So actually training, I will discuss something about training. Most of our presentations are about inference. Okay, most of the accelerator that we are discussing, they are for inference. Very late in the course, if time permits, we will discuss about training also. So if you're interested, you can see this paper.